Before we start on that program, I wanted to actually call here on stage Denis Vrenko. Denis, as you know, is the person who's actually flying something on this rocket. He's flying a logo, okay? And that's his logo. There was a competition organized by ESA on, we usually do that on having actually a design that we paste prominently on the rocket. And Denis won that competition and produced that logo. And I was wondering, you know, what inspired you to actually create that logo?
Yes. Hola. That's my Spanish. There was a competition, and there was a lot of time in this competition, but I just found out about it 1 week before it closed. But on my luck, they kind of extended for a couple of weeks, so I have had time to do the logo. My inspiration came from of course, studying what this beautiful satellite will do, and then learning what actually that means and what it does. So it uses this light stuff to measure transiting bodies around the stars. And that's what I try to represent with the way the satellite sees it is like a very bright spot and some smaller, the light that's not there anymore. So with that difference, it can detect how big are all the science stuff and characterize the planet. And as if we would look at the stars like the Cheops with our eyes, we would see the bright spot with small black with no light spots on it. So the different colors are the different stars, and the black spots are the planets transiting them. And the colors try to represent the vastness of the stars we will look, so different stars, different colors. And that's my inspiration. And I'm from Slovenia, we're here, like, we have a flag there. It's a bit to the side, we're not a member state, but we're like cheering you guys on, so thank you.
Yes, I should have mentioned. Thank you, Denis. In real life, Denis Vrenko is actually an architecture student in Ljubljana, in Slovenia. Slovenia is an observer state at the moment, and we hope that it's going to be a member state in the near future. I was born in Switzerland myself, so this reminds me more of a Swiss cheese. I think it's very fitting for a Switzerland mission, but I love the logo, and I think I will need to switch my association to these transiting planets. And obviously you see the richness and the variety. So I like this logo very much, one of my favorites as well. Good, so I want to welcome you again here at ESAC. I'm the head of science and operations, which means that I'm relaxed because I'm in charge of managing all the space missions, but only once they're commissioned. So until it's launched and really in space and commissioned, it's somebody else's responsibility. So I'll take over as soon as we have commissioned this mission, which is going to be sometime in January, and then it will actually come into our overall responsibility. But as I mentioned, for this mission in particular, it's going to be operated, actually it's going to be even more relaxed for us because the mission operations are done by INTA and the science operations by the University of Geneva, so just very briefly, if you're not familiar with ESA, just a couple of facts. It's 22 member states. You could see all the flags down here, plus Slovenia as an observer and Canada as an associated state. We have about 5,000 employees, not here all on site. We have about 400 people here on site at any given time. What is the European Space Agency? We're actually exploring and use for space, but exclusively for peaceful purposes. We have our headquarters in Paris and then 7 sites across Europe, this being one of them, and a spaceport in French Guiana. That's where Cheops sits at the moment, waiting for the engineers to give it green light. And so what is our budget? Pilar and both Rafael mentioned that we just had a ministerial conference which decides about your 3-year funding. We are very proud to this time that we got such a vote of confidence with 12.5 billion euros for the years 20 to 22. But if you actually shift that to a member state contribution, so what you and I contribute every month is a bit less, it's actually 70 cents. So you contribute a little bit less than €1 per month to us, so thank you very much. And if you go to our webpage, this is what you would encounter. We're usually doing serious stuff, but sometimes also allowing us to smile. We have 4 basic pillars at ESA. We have the space and exploration, and science and exploration, that is which we are part of. We have also safety and security. We have applications. We have enabling support. But really what we're talking about today is science and exploration. So it's on the one hand the Directorate for Science, which is heliophysics, planetary and astrophysics missions. On the other hand, human and robotic exploration, which we are collaborating with but not part of. And inside this program, all the science missions are operated from here. So you are here in this building, actually on the back of the campus. You entered this morning from the bottom and then walked your way through. And we this site saw an evolution. It was first a ground station with antennas. It then started to actually operate some missions and now became really the heart of the Directorate for Science at ESA, and we are managing all the science missions from here. We still have a very large technical group at ESAC in the Netherlands, of course, but eventually when the missions are producing science, this is where it's managed from, and also where our archive sits in the main building here in the center. And what are we launching? So you see that this is our entire fleet of satellites. To give you just a very brief overview, at the top I'll show you 2 slides. One is our solar system explorers and the other one is the cosmic observers, and they're both structured in the same way. So at the top, these are the missions to come, so the ones which are getting ready to actually get into operations. And then in the middle row is actually all the missions that are flying at the moment. So you see that in the solar system we have quite a few orbiting the sun, on their way to Mercury, orbiting the Earth. We have 2 missions at the moment orbiting Mars, and we're preparing actually to launch in 2 years the one which is going to take us to Venus. And then once they actually did their work, they're actually getting here in the legacy phase. So these are the missions for which are not operating anymore, but where we host the data, we nurture the data, and we actually the memory of for humankind of these data, which we will curate for another 100 years or so, or longer. I think Christoph is somewhere in the audience here who's managing this. So, and similarly, we have a program which is looking beyond the solar system, same as a row of exciting missions that are just about to actually start there. Cheops, you see, is just making its transition from the top row, being in development, to being operational, so that will happen this week, and then we will take it over. And as there, we're flying some really key missions. I'd like to mention, of course, the Hubble Space Telescope that we are together with NASA operating, which is, I think, iconic mission now. It's I don't think you can run into anybody, certainly in Europe or in the US, who doesn't know what the Hubble Space Telescope is. Gaia, which we are very proud of, because last year, or actually this year, it broke the record of scientific publication of a mission in a year. It published more than 1,000 papers. And Cheops is going to join now this family, which also has XMM Newton, which just celebrated its 20th anniversary, and another high-energy mission, Integral. And of course, a number of missions that have flown that we're very proud of, and whose data we actually still nurture and curate. So that's essentially what we're doing, a large fleet. Cheops is one. You'll hear what the Cheops context, a little bit more about the Cheops context from Anna in a second. So who's behind Cheops? You heard that, so I don't need to mention it. I'll just repeat it very briefly. It's essentially a dedicated consortium with 11 member states. It's led by the University of Bern. ESA, the role of ESA in this is really the mission architects who are responsible for the procurement and the testing of the satellite, for the launch and early operations. So this is why we're not taking any risks. We don't want to spoil with the launch the work that the other member states have done. And the prime contractor, you heard also from Pilar here, was for the construction of the spacecraft of Airbus Defence and Space in Spain, but many more contributions from Spanish industry and various parts of the satellite. And finally, as I mentioned already, the mission operations are going to be done by INTA in Torrejon, so just less than an hour drive from here. And the Science Operations Center will be located in Geneva, Switzerland, which is my birthplace, so I'm very happy about that. Raphael mentioned already these two, so it's very timely indeed. I think in this case, Europe had a great intuition of moving into the right science field. We knew that it was going to be very exciting to study exoplanets. This is why I think 5, 6, 7 years ago we took the decision to select Cheops as a mission, and Cheops is the first of 3. And we know what the other space agencies are doing, and indeed they're not doing, actually they're not doing anything almost as dedicated exoplanet missions. So Europe is really taking the lead here. And I think it was very fitting, we didn't plan it of course, but that exactly this year we had for the Nobel Prize in Physics 2 Swiss laureates, Michel Mayor and Didier Queloz. And Didier is actually today in Kourou, so he witnessed live, he will stay until tomorrow I assume. This is a picture taken from 10 days ago when they were both in Stockholm getting their medals, well deserved. And that, of course, is not a one-off. We knew that actually Europe, and in particular Switzerland, were leading the field of exoplanet science since over 20 years. Good, so what is Cheops about? You'll hear much more about this, but make me just make the one punchline. It's not about finding exoplanets. We had a number of missions in the last years which did find exoplanets. We know now of thousands of exoplanets, so we know that our solar system is absolutely not unique, something which if you're as old as I am, you didn't learn at school. At school, at least when I still went there until the end of the 80s, it was clear that, or it was not clear whether there's any other solar system existing. Now we know that there are thousands, and statistically that probably every single star, at least every second star has a solar system in the sky. So look up tonight, and that's the number of solar systems at least that you have around you. But now we really entered the next phase. We really want to actually understand what type of planets are they, and Cheops is actually the first mission to characterize them, and you'll hear from Davide and Laetitia how this will be done. So it's really essentially on the past. What we really want to answer in the end is the question, are we alone? Really, our goal is to find life. It's a long and complicated path, but we're getting very close, and I have good hopes that in my lifetime we'll still find life. If not, my kids and my grandchildren will study it extensively. So it's going to be very exciting, and Cheops is one step towards that. So here's the program for this morning. The times will all be pulled forward a little bit, roughly half an hour. We'll have Ana Eras, who's the Plato project scientist. So for the next exoplanet mission, the Cheops project scientist is actually down in Kourou. She's witnessing the launch live. But Anna will tell us a little bit how the mission fits into the ESA program. We have Francesco Ratti, also from ESA. He's actually the instrument, sorry, I put here scientist, but he's actually the engineer. So he's been working for the last 6-7 years on Cheops, and can tell you a little bit how Cheops was built. We have Laetitia Delray, who's actually from the Cheops science team, from the University of Liège, and she will tell you a little bit what the diversity of exoplanet is and why we're doing this. Davide Gandolfi was assigned by ESA to the science team and is going to tell us how Cheops will investigate these exoplanets. And finally, we have Isabel Rebolledo, who's actually a principal investigator. That's Raphael mentioned it briefly. The science team has a large program that they want to execute. They have a number of planets that they want to observe, but we left a window open for anybody who has a good idea to actually propose it and actually join the mission. And Isabel was one of these people, and will be looking for exocomets with Cheops and tell us all about this. So this is the program that we'll follow. We'll have a question and answer session afterwards. And so for me, just thank you for being here with us today, and we'll have plenty of time to answer questions after the talks. And I'm then just going to move to the first speaker, to Ana Eras. Ana Eras is a project scientist for Plato. She is working at ESA. Usually she's at ESAC in the Netherlands. So thanks for coming down here. And you will tell us all about Cheops in the context of those 3 missions that we are planning in the next years. Please.
Okay, so thank you very much, Marcus. Well, I would like to add that I was also study scientist for Cheops, so Cheops is also close to my heart from the point of view of my previous work, and also for the work that I do in general in exoplanets. Okay, so 4,104. These are the number of exoplanets that we know today. But what do we really know about them? What do we really know about these exoplanets? If we plot in a figure the size of the planets that we currently know, and for which we have the radius measurement as a function of the distance from the star, and in this figure we also show the planets of our own solar system, like you see here. So, in particular, the small ones. So we have here Mercury, Venus, Earth, Mars, and the giants. And then we see that the planets that we have discovered, they are in general quite different, at least in their distribution of radius with respect to the distance to the star than the planets of our solar system. So in particular, we have found planets that are as big as Jupiter and that they are orbiting very, very close to the star, and then they are in orbits of periods of days, and we are calling them hot Jupiters. We've also found planets that have sizes between the Earth and Neptune, and these planets don't exist in our solar system, so we are very curious about them. We really want to know what they are made of. We really want to know how they form. And also this will teach us how our solar system will form, looking at the diversity of these exoplanets and comparing to our own planets. But in order to understand and to know what these planets are made of, so the first parameters that we need to know is how big they are, their size, and we also need to know their mass. Because if we have their radius and their mass, then we can derive their density. And depends on the density, we can establish if these planets are, for example, gaseous planets, because their density is very low, or they are planets that are made of water, or are they planets like the Earth? Maybe they have an atmosphere of thick hydrogen that prevent that life develops. And in order to learn all this, indeed, we need first to know the radius and the mass of the planet. But the current situation is that we don't know most of these parameters for most of the planets. So in particular, if you look at the ones for which we have the radius, for most of them, we don't have the mass. For those planets for which we have the mass, we don't have the radius. And even in those cases in which have the radius and the mass, so the measurements that we have of these characteristics are not precise enough to give us a good impression or a good idea of what the composition of the planet is and how the atmosphere is. So this is what we need Cheops. So Cheops, as has been said, of course, already, is a mission that will follow up stars and will follow up planets that we know that exist already. And especially will concentrate on bright stars. Because if you have a bright star, then you can derive the mass, because to derive the mass normally from the ground, it needs to be, the star needs to be bright, we need a lot of photons. And then if you have a bright star, you can also determine the radius with much better precision. So that's why Cheops will concentrate on bright stars, will determine the radius with much more accuracy than we know until now. And then with this, we will be able to determine the composition, the characterization of the exoplanet, and then we also derive other characteristics that further on will be explained in the presentations that come after mine. What is also important is that Cheops will provide characterization and therefore will be able to identify golden targets for spectroscopy and then for further characterization with other observatories. It will be able to show us which planets are more similar to the Earth, for example, and then in which planets have maybe thick atmospheres, that these are less interesting to be follow up or interesting from other points of view that is not the development of life. So basically, this is one also of the main aims of Cheops. Cheops will use the transit method that is based on very precise photometry. So we look at the star, we look at the intensity of the star, and when the planet passes in front of it, there's a decrease of the intensity. And then this decrease of the intensity of the star is proportional to the square of the ratio of the radius of the planet and the radius of the star. By knowing the radius of the star, then therefore we can derive precisely the radius of the planet. And that's why this method is so powerful, because it can give us very, very precise measurements. Well, clearly, this I think that we all know already that Cheops is a small mission, and is the first small mission in the Cosmic Vision program of ESA. It's been in partnership with Switzerland, and then Switzerland, through the University of Bern, leads a consortium of 11 countries, and they have provided the payload and the mission operations. And in order to meet the constraints of a small mission, so Cheops had obviously to be based on mature technology, and be based on technologies that so they were controlled enough that allowed a cost a cost of 50 million euros to ESA, and then also a short development time. And the development time, now you can see that the proposal was selected in November 2012, and then now we are here, and tomorrow or the day after tomorrow, waiting for the launch. So then this is a very short time in comparison with the missions that we develop in ESA as medium or large missions. Okay, so the launcher is a Soyuz launcher, and we have Cheops will be launched into a sun-synchronous orbit. So this is Cheops here. So it will go through the poles. It will take only 100 minutes. It will only take 100 minutes to go around the Earth. And in the way that the satellite is oriented, it will always have the solar arrays looking at the sun and the telescope looking at the dark sky. Obviously, so to avoid any stray light that could contaminate the measurements. Okay, so then the science program of Cheops is 80% defined by the scientists that are directly involved in the mission. So then there's the science team, and then we have here also representatives of the science team and the consortium. But there's still 20% that is open to the worldwide scientific community. And then this 20% is assigned by ESA through calls, through announcement of opportunity that anybody, all scientists in the world can apply for. And then there's a time allocation committee that decides if the proposals are worth of the time of Cheops or not. And the next step, I wanted to put Cheops indeed in the context of previous, current, and future missions. So first, we have the ground-based observatories. Well, clearly, the ground-based observatories are very important for all exoplanet science. The first exoplanet was discovered in a ground-based observatory, and then we continue making major advancements there. Especially for the determination of the mass, this is very important because most of the masses that we determine the exoplanets are measured on the ground. And then we have missions that have been dedicated to exoplanets. So we have the mission Corot, that was a CNES mission, and then with participation of ESA. Then we have Kepler, that is a NASA mission, and these two missions are not in operation anymore. And now we have TESS, and TESS is a NASA mission that is indeed operating, that is looking at the whole sky, looking also for transits of exoplanets, so discovering new exoplanets. Very important, there are missions that are not dedicated for exoplanets. There are more general purpose observatories, so they have other objectives, but they have contributed also in a very important way to the development of the exoplanet science. And one is the Hubble Space Telescope, then we have Spitzer, an observatory in the infrared. So then Hubble is an ESA mission, Spitzer was a NASA mission, and then we have Gaia, and then we are still waiting for the results from Gaia, but it will also provide interesting science on exoplanets. And then, so here we have Cheops. In the future, we have very important also the launch of the James Webb Space Telescope. We have Plato next, and then we have Ariel. And it's also very interesting to consider that Cheops will be operating in parallel to TESS and in parallel to the James Webb. So basically, some of the important targets or the interesting targets that TESS will discover, maybe with less radius accuracy, will be followed up with Cheops, and then Cheops will be able to provide maybe interesting targets to JWST. Okay, so follow up this one, look at the atmosphere of this target, because maybe there we will find molecules that are very interesting from the point of view of formation of exoplanets and maybe even habitability. Okay, so just going to these future missions. So indeed, the James Webb Space Telescope. The James Webb Space Telescope is a joint mission between NASA, ESA, and the Canadian Space Agency. It's going to be a major observatory. It's the largest telescope launch in space, 6.5 meters. It's a general purpose observatory. It will tackle all areas of astronomy and cosmology, but it will also make major contributions to exoplanets. And then in particular, it will be able to do detailed characterization of the atmospheres of many of these exoplanets with spectroscopy, so looking at the different colors of light. They will look at molecular signatures and atomic signatures in the atmospheres of these exoplanets with a lot of detail. And it will also be able to do direct imaging for some of the exoplanets. So some of these exoplanets, then we will be able to make pictures, basically, with the coronagraphs on board JWST. The launch is scheduled for March 2021. So then we'll have to wait now still for, well, 1 year and a half more or less, but it's really coming very soon. Okay, so the next mission, indeed, the mission that I'm working on for some years now, and this is PLATO. And PLATO, actually with the acronym, it already says a lot, is Planetary Transits and Oscillation of Stars. And the main objective of PLATO will be to discover new exoplanets, and in particular will focus on terrestrial exoplanets orbiting up to the habitable zone of bright sun-like stars. And the habitable zone here we define as the distance from the star in which water can exist in liquid form on the surface of a planet. So this has implications, obviously, for habitability. And it will not only discover new ones, but what is very important is we'll be able to characterize them very well, determining the radius with the transit method, the mass also combined with the ground-based observations, and also the ages. And the ages, it will be able to determine because PLATO will also measure the oscillations of the stars. And with the oscillations, we'll learn about stellar evolution, we'll learn about the stellar structure, and then this will give us the age of the star and therefore the age of the planet. So then that's why it's very important. It is connected also to the science case of Cheops, of course, is bright stars. And with bright stars, we can determine much better the characteristics, starting with the masses and the very precise radius. And the launch of the PLATO is 2026, and it will operate in a different way as Cheops. Cheops looks at one star at a time. But Cheops, because he wants to discover new exoplanets, will look at large areas of the sky for a very long period of time, and then we'll wait until the planets come in the front, and we'll observe around 100,000 stars simultaneously in order to discover these new exoplanets. And the next mission that has already been approved is Ariel. Ariel stands for Atmospheric Remote Sensing Infrared Exoplanet Light Survey. And I think the acronym already says a lot of what the mission is doing. And indeed, Ariel is dedicated at performing atmospheric characterization of planets that we know they are there already. So you see how all these missions complement each other. So with PLATO, we will discover new exoplanets, and then with TESS, we are discovering now new exoplanets, and all these will be followed up. So we see JWST and also with Ariel. So Ariel will be dedicated to performing a chemical census of planetary atmospheres, because it will be able to look at a large sample of planets, and then these planets will range between the size of the Earth to the size of Jupiter, and the launch is now planned in 2028. Okay, so I just wanted to finish with But we are talking about the future, basically. And the future, of course, is already the new generations, is children. And so that's why I wanted to show here one of the 2,748 children's drawing that have been engraved in plaques in Cheops. And actually, they are also going to be launched, these drawings. And well, since we are in Spain, I have chosen the drawing, a beautiful drawing of Cheops, of a Spanish child in particular. And I think that, well, this is a very, very good example of how our missions are also a source of inspiration to the new generations and a source of motivation to continue watching space, continue being involved in space, and also to continue learning about our place in the cosmos. And with this, I finish. Thank you for your attention.
Thank you very much, Anna. So let me ask you, I mean, you've James, Cheops, James Webb's, Ariel, Plato. Do you have a favorite?
They're all fantastic, but okay, Plato for me obviously is.
All right, but Plato is 2026, if I... 28. Okay, good, thank you very much. So as the next speaker, we have Francesco Ratti. Francesco is actually an instrument engineer, also working for ESA, usually at ESAC. And he has accompanied actually Cheops through the entire technical development, and he's going to give us a little bit an overview of how to build Cheops and a bit of behind the scenes what it takes to actually get a satellite built and launched. Okay, here, Francesco.
Hi. Hi, hello. Thanks a lot, Marcus. Also, thanks a lot for having called me scientist. I really feel honored, but unfortunately, I'm just an engineer. And in the last 6-7 years, I've been working on Cheops, so I would like to tell you a little bit how we went along the building of Cheops, what are the challenges, and I would like to show you also some nice picture. So, as it has been said before, working in Cheops is really meant working with the team from Europe. In particular, 11 member states have contributed to Cheops, and just as it has been mentioned before, the leading role of Switzerland. So from ESA, we worked hand in hand with our colleagues of the University of Bern, who are leading the instrument consortium, and also from our colleague from University of Geneva, who are providing the science operation. Also very important contribution from Spain, with the spacecraft led by Spanish industry, and with the Mission Operations Center, which is in Torrejón de Ardoz. Actually, it is 11 member states. If you think about it, it's half of the member states of ESA, so it's quite good for a small mission to have such a composition of member states. So normally when you hear about transit photometry, you see this picture. It looks actually quite simple. You have a star, and if a planet is in front of the star, then you will see some reduction of the light. So indeed, it seems very simple. When I explain to my kids, they tell me it's very easy. But when you try really to measure it, it's very complex. It's very, very difficult measurement. In the past, it was believed that actually it would have not been possible to see a transit in this way. So how does it look like a real measurement? You see this cloud of points that are here, these gray points, and each of these points is actually a measurement. And what is done is these points are averaged, so you see this red dot line, and by connecting then this red dot line, you really get these light curves, and you can understand if a planet has transited in front of the star or not. So each of these points is actually coming from one measurement, one picture. This is how a picture of Cheops will look like. So what you see in the center is the star, and what is done is called photometry. So there is a window around the star that is placed around the star, and all the intensity of the light that is in this pixel is counted, is summed up, and this makes one measurement. So it's really important that the instrument is stable in order to count accurately all the light in the, coming from the star. So again, it's an extremely small signal variation. We are talking about part per million. So in order to see a planet like Earth, you have to measure with an accuracy of 20 part per million, which is 0.002%. So it's extremely small. So what you see here is a section of the instrument. So how does it work at Cheops? So the light from the star that is under observation is coming to the telescope. This is the light beam, which brings with it the information on the planet. So the light travels through the telescope, and it hits the mirror 1, which is at the end of this baffle. Then the light is reflected, is focused on the mirror 2, which you see here in this position, and then from the mirror 2, it goes through another inner baffle, it goes to a set of lenses and a folding mirror, and then is focused on the detector, which then provides this image. So the size of the mirror 1 is 30 centimeter, so it's quite a small mirror. So Cheops is not about size, but is about accuracy and stability. And the length of the baffle is a little bit less than a meter, and the baffle is there in order to be able to select the light from the star and only that one. This is very important because otherwise it would not be possible to measure with such accuracy. So this is a picture of the baffle. You see it's very dark. When you look into it, you almost cannot see the veins inside. And this is a front picture. And as you can see, what is imaged on the mirror is really what is in front of the telescope, what is in the front of view. And I would like to mention also that this baffle has been done based on the experience that we got from Corot baffle that performed quite well. Corot was the first mission that was launched in 2006. And for me, it was very special to work on this baffle because when I joined the agency, one of the first tasks that they gave me was indeed to work on the Corot baffle. So it was very nice for me to work some years after again on a baffle and to use all the experience that we gained for Cheops. And also, this is a picture that we took a few weeks ago during the launch campaign. You see here Cheops that is encapsulated inside this structure. This structure is from the launcher and is the structure that then supports the primary passenger, which is on top. So this was the volume that we had available was inside this structure. And as you can see, Cheops really just fitted in nicely in the structure. So we really used all the available volume, all the length available for the baffle to really, indeed, to have a longer baffle as possible to reduce the stray light on the telescope. So it's important to have a very accurate and very stable telescope. So what you see here is a photo during the integration. This black structure is the telescope tube, which is done in carbon fiber, and the carbon fibers was laid in such a way to reduce every possible deformation during operation. So first of all, we selected very stable material, but not only, we also have a thermal control that keep the temperature of the telescope constant. Here you see a picture of the outer tube, which is placed around the telescope tube. The temperature is monitored, and then there are heaters, and in case the temperature varies, in case the temperature sensor show a temperature variation, the heaters are there to keep the temperature constant. This is a picture of the outer tube that is then aligned and lowered on the telescope tube. This is a nice picture of the mirror 1. You see it on the back is actually lightweighted to reduce the weight of the mirror. It's in a special glass called zero Dur that has a very low coefficient of thermal expansion. And you see also here in the center the mirror, through the hole through which the light goes after the mirror 2. And this is a picture of the mirror with the silver coating applied, which is very reflective. So just a few words on the eye of Cheops, which is the detector. It's working very cold at minus 40 degrees, and it is kept at a very stable temperature to less than 10 millidegree. Here is a picture of the detector, and again is a small detector. Again, Cheops is not about size, but is about accuracy and stability. So it's a small detector, and we went to really extensively characterize and test. Maybe one thing that you don't realize nowadays, we all have a mobile, we all take a lot of pictures. On the detectors that are normally available, there are a lot of pixels that are actually not working. We don't realize that because there are megapixels, so few pixels that are not working is not affecting the image. But for our application, it's really important that all the pixels are working and in a controlled way. Otherwise, it's not possible to measure such a small variation. So we went to pick up the best of the detector from the lot, and then we characterize. Here you see, for example, how the detector is sensitive to the different colors, to the different wavelength of lights, and here are characterization of the sensitivity with respect to detector setting. And this is a picture of the focal plane module where the detector is located. Here you see the detector in the center of the focal plane module, and also in order to thermally insulate, there was a small piece done that really reduced the thermal conductivity coming from the structure. So one thing that also we didn't have much in Cheops is time. We had limited time. So you might have noticed that the Cheops satellite is done actually nicely in two parts. There is the instrument, which is mounted on top, and then there is the platform structure, which support the instrument, which is below. This has been done on purpose in order to allow a parallel development. And what I would like to show you here is a moment of the mating of the instrument with the platform. So what you see here is the platform. Here we are at Airbus in Madrid, in the integration room of Airbus. What you see here is the flight model of the structure, this hexagonal shape, and you also see this panel is open, and the unit that is on this panel is actually the onboard computer. And this is the moment where the instrument is coming, is integrated on the platform. Oh, if I manage to, okay. So the instrument in this moment has, first of all been integrated fully and tested by the instrument consortium, and now is coming in one single piece. So we had this red part, which was really acting as connecting the different elements of the instrument to allow really to mount it as a single block on the platform. And as you can see, the operation indeed went quite smooth. So first there was then the mechanical integration on the platform, and then the electrical connection so that the instrument computer can talk to the onboard computer.
They work very fast.
Indeed, we work very fast. Yeah. Actually, it was also very interesting to notice that on the background, here you see, this is actually the structure of Ceosat, the Spanish Earth observation satellite. So indeed, it was a very busy moment at the time because they had these two satellites in the clean room. Okay, just a few words more on the platform. As you can see here is an hexagonal shape, and it includes all the equipment like the communication, propulsion, pointing, and the challenge here was really to adapt to fit inside the Soyuz launch. And also the solar panels, as you can see here, are part of the structure. So this is a moment of the integration. Actually, the first thing that went inside the platform was the harness. This is because it's very packed. There are several units, and they have all cables interconnecting. So the first thing that went in was the harness. This is a nice picture of the tank, the 30-liter tank, which sits nicely in the center of the platform. This is a picture of the antennas, the transmitting and receiving antenna, which are sticking a little bit out from the satellite, and indeed we hope to use it soon, not today, but as soon as the launch is done, to communicate with Cheops. And this is a picture of the solar panel. You see the solar cells, and the solar panels act also as a shield for the instrument that you see mounted here on this side. So after mating the instrument with the platform, then we went to extensively testing the Cheops satellite. So what you see here is a vacuum chamber. We placed the satellite into the vacuum chamber to test it for the vacuum of space. But not only that, we had also heaters to simulate the illumination of the sun, and also cold shrouds to simulate the condition of deep space. Here you see a nice picture of Cheops on the shaker. It was vibrated before launch, indeed, to check that it can survive the launch environment, the launch loads. These are nice pictures that were taken a few weeks ago. This is the fueling of the satellite, of the tank, and since the fuel is an hazardous material, you see these colleagues had this special suit, and they took a lot of care during this operation. This is the encapsulation with the structure of the launcher, which is lower down on Cheops, and then on top was placed the Cosmos SkyMed, and this is finally the fairing of that includes the stack with the Cheops, with the Cosmos SkyMed and the auxiliary payloads just before being brought to the launch pad to be mated with Soyuz. And here you see the nice drawing of Dennis on the fairing. So indeed, to conclude, thanks to the Cheops team, indeed in Cheops there has been a science team which has set up the objectives, prepare the exploitation of data, and will be looking at the data as soon as it is available. There has been a team of engineers that went out and designed the instrument and the platform. And I would like also to give a special thanks to the engineer and technician that in the clean room assembled the instrument and the platform. It really took a lot of care and a lot of attention to make sure that the satellite is ready for the launch. And also I would like to mention that we did also quite some outreach activity. Here you see our project scientist, Kay Isaac, while she was explaining Cheops to the general public during one open day with a model of the transit and some nice picture. So we really spent some time to communicate this project, and we really hope also, thanks to the work of the journalists, that we can communicate this project, and this can be inspirational for the next generation to understand, to go on and understand more about our universe. So thanks for that, and indeed keep watching, because we hope then to be able soon to communicate with Cheops once that is in orbit.
Thank you very much, Francesco. Let me ask you one quick question. You said you worked on the buffer and especially on the cover, right? So actually this cover will open only in January sometime, because we were going to launch the satellite and first test it out. So if it does not open, Cheops will not see stars. So how long will you stay nervous?
Yeah, I think I will stay nervous probably, well, until mid of January. Indeed, it will not be really the first thing that will be done during the commissioning. First, we will take some picture actually with the cover closed, this in order to have some dark images on the detector. And then indeed, after more or less 1 week of in-orbit commissioning, then once that we are sure that everything working fine, then we will open the cover, we will break the frangi bolt, and indeed the cover.
And then you will sleep peacefully again. Okay, good. Thanks again.
Thanks again.
As a next speaker, we have Laetitia Del Rey, who's from the Liège University. Laetitia is actually part of the Cheops science team, so the team which actually defined the science, the core science of the Cheops mission. And she will tell us a little bit about the diversity of exoplanets and what Cheops will actually look at, and the context of what we know about planets in other solar systems today. So, Laetitia, please.
Yeah. Thank you. Good morning, everyone. Can you hear me well? Yeah, cool. So I'm very pleased to be here with you today to tell you a bit about the diversity of exoplanets. And as you know, this is really an exciting, exploding field of discovery, and I will try to give you a little sense of that this morning. So let's go on that journey. So it has been almost 25 years now since the discovery of the first exoplanet around the Sun-like star in 1995. And this pioneering discovery really kicked off an era of exoplanet hunting. So what I'm showing you here is the cumulative number of exoplanet detection over the years. And as of today, we have found more than 4,000 exoplanets. So this is a bit crazy, and we keep finding new ones almost every day. Now you can see this is color-coded according to the different detection methods that we've used. And actually, you can see that 2 methods have been particularly successful at detecting exoplanets, which are the radial velocity and the transit method. So I'm now going to give you some background on these 2 techniques. So the radial velocity method is the one that was used to detect the first exoplanet. So when a planet is orbiting around the star, it actually makes the star wobble a little bit as a reaction to the planet's motion. And this wobble will have an impact on the light that we can observe from the star because of the Doppler effect. So when the star is moving towards us, its light will appear slightly bluer. And when the star is moving again away from us, its light will appear slightly redder. And so by measuring these tiny changes in the color of a star, you can actually deduce the presence of a planet around it, and you can also measure the mass of this planet, which is the first very important piece of information if you want to know what type of planet you're dealing with. Now, if you're lucky and your planetary system is almost perfectly aligned with your line of sight, then the planet will pass periodically in front of the star once every orbit. And what you will see in this case are some small dips in the brightness of the star when the planet passes in front of it and blocks some part of its light. So by detecting and measuring precisely these dips in brightness, you can not only deduce the presence of a planet around the star, but you can also measure precisely its radius, which is the second very important piece of information you need to characterize an exoplanet. Now, by using these detection methods over the past 2 decades to search for exoplanets, we found out that they're actually everywhere. So on average, almost every star has a planetary system of some kind. And these thousands of exoplanets we found were nothing like we expected based on the planets of our solar system. So let me show you a few examples. So the first type of exoplanet we found are what we call hot Jupiters. And we call them like that because they are Jupiter-like planets, so big gas giant planets. But unlike Jupiter, these ones are orbiting extremely close to their star, so they are extremely hot. So hot that their atmosphere is actually boiling off, whipped away from the planet and forming some kind of big tail behind it, as you can see on this artist's impression. Now, we didn't just find big hot planets, we found some small hot planets as well. And this is a new type of exoplanet that we call lava worlds. So these are some small rocky planets, which again are orbiting extremely close to their stars, so they're extremely hot, thousands of degrees. And their surfaces are actually so hot that they can melt rock. So we think that these worlds are covered with lava. That's why we call them lava worlds. Now, another type of exoplanets we found are super-Earths. So these are some planets that are bigger than the Earth, but less massive than Neptune. And we don't have any planets in this size range in our solar system, but they appear to be extremely common in our galaxy. This is actually the most common types of exoplanets we found so far. And we're still not sure what they're exactly made of. Are they scaled-up version of the Earth, so big rocky planets, or are they some ice giants that got smaller somehow, so some kind of mini Neptunes? We don't know. And actually, this will be one of the main science goals of Cheops, to better understand the nature of these very common exoplanets. Now, we didn't just find very diverse types of exoplanets. We also found exoplanets in very diverse situations. So you have here a famous scene from Star Wars where you can see Luke Skywalker watching a double sunset on Tatooine, his home planet. Well, we actually did find some exoplanets that are orbiting not one, but 2 stars. So this is not science fiction anymore. Now, to give you a bit more a global view, what I'm showing you here is the currently known exoplanet population in a diagram of the planet radius on the vertical axis against the orbital distance on the horizontal axis. So this is the distance from the planet to the star. And I've also shown some of the planets from our solar system for comparison. So you have here the Earth, Neptune, and Jupiter. And what I would like to emphasize here is really the astonishing diversity of exoplanets, both in terms of dimensions and orbits. We found Jupiter-like planets on the whole range of orbits, from very close in orbit here for the hot Jupiters to very distant ones for these planets here, which are orbiting their star much farther away than Jupiter is from our Sun. You can also see here a whole bunch of planets, which are the super-Earths and mini-Neptunes I just told you about, which appear to be the most common type of exoplanets in our galaxy. And it's fair to say that these empty areas here in this diagram are empty not because they are unpopulated, but just because our detection methods are not able to reach them yet. Now, a question that follows naturally when you look at this diagram is, okay, we found plenty of exoplanets, but among these exoplanets, are some of them habitable? Well, we actually did find about 50 exoplanets now that are orbiting within what we call the habitable zone around their star. So this is the region around the star where a rocky planet with an atmosphere could have some liquid water at its surface. And we are particularly interested by liquid water in the context of habitability, because this is a key ingredient for life as we know it on Earth. So within the habitable zone, in green here, the temperature is just right for liquid water. Closer to the star, it's too hot, and further away, it's too cold. And you can easily understand that the location of this habitable zone around the star depends on the type of star you're looking at. So for hotter stars, the habitable zone will be much further out, while for cooler stars, the habitable zone will be closer in. Now, just something I would like to stress here, because I think this is important. This is not because a planet is orbiting within the habitable zone around its star that it's necessarily habitable. There are plenty of other factors that are important to take into account when assessing an exoplanet's habitability. For example, does it have an atmosphere? What's this atmosphere made of? What's the level of activity of the star, and so on. But okay, we have to start somewhere, and this concept of habitability is very handy to narrow down our search for potentially habitable worlds. And one of the most famous celebrities in this category is the TRAPPIST-1 system. So I had the chance actually to be involved myself in the discovery of this system. And I remember that with my colleagues, we first couldn't make sense of the data we were getting, because almost every day we would find a new transit in the data. And this transit would be slightly different from the previous ones. And we were also getting some very weird signals with very weird shapes that we later understood were actually due to several planets transiting at the same time in this system that now we know today counts no less than 7 transiting Earth-sized exoplanets. And these planets are orbiting what we call an ultra-cool star, so a star that is very small, very cool, very dim. And you have it here represented with compared to the inner solar system. And you can see that the TRAPPIST-1 system is extremely compact. Like all 7 planets fit well within the orbit of Mercury. But because the star is so cool and dim, the planets are actually not so hot. They have all temperate temperatures, and 3 of them are orbiting within the habitable zone. So this is one of the most exciting systems we found so far for future characterization studies of potentially habitable worlds. Because, of course, now that we found all these exciting exoplanets, we want to know more about them. We want to know what they are made of, how they formed, if they have an atmosphere, what's the composition of this atmosphere, what are the conditions at their surface, and so on. And so with Cheops, we are now moving from an era of exoplanet detection to one of exoplanet characterization. And we can also look forward to exciting times ahead with the future missions you've heard of earlier today, such as the James Webb Space Telescope, Plato, and Ariel. And I will just end with some of the big questions that we would like to answer now that are driving the field, and also me personally as an exoplanet scientist. So first, what are exoplanets made of? How did they form? How did they evolve? And if we want to know that, this is also to be able to place our solar system in perspective, to understand how it fits in all this exoplanet diversity and how unique it is. Right now, it looks like it's pretty rare because we haven't found any proper analog yet, but this may change in the future. And of course, all this is also very important in the context of the search for life elsewhere. So we are now really looking forward to the Cheops data because they will help us addressing some of these questions, as Davide will now explain you. Thank you.
Thank you very much, Letizia, for showing us a little bit the diversity of planets. A quick question while Davide is setting up. If you had a choice of living on one of these planets, which one would you pick?
That's a
Tatooine?
No, I think I would still pick TRAPPIST-1e, so one of the TRAPPIST-1 planets that is within the habitable zone. Yeah.
So that's cool because
maybe the night side, because I don't want to get too much.
And a year takes about a few days, right? So it's your birthday every week there. So that's why you pick.
Yeah, that's really cool. Lots of birthday presents.
Not a bad planet to live on. A birthday every week. Okay. We move on to Davide Gandolfi. Davide is from the University of Torino. He's also a member of the Cheops science team. He's an ESA appointed member. So what does it mean? So when a mission actually defines a science team to define the core mission, of course the lead institutes are have scientists which are contributing to that. But ESA is always very keen on having the entire member state community contributing, and so we make open calls and look for actually volunteers to see who else wants to contribute. And Davide is one of these people who actually said, you know, I would be a good person to participate, and we were absolutely convinced by that, and that's how he joined the mission and is now helping to actually define the science that Cheops is doing. And he will tell us a little bit about exactly how Cheops is going to do the science that it's going to do. Davide.
Thank you. Hi, everyone. I'm very honored to be here. I will be talking about the science that Cheops will be doing, and I will show how Cheops will be doing that. But before I start, I would like to try to put Cheops in context, and I actually like to start from the very, very big picture. This is our galaxy, the Milky Way, how it looks like from an observer inside the Milky Way, which is the Sun, the Earth, the solar system. So you basically see the plane of our galaxy, and you can see here in the center, in the middle, the bulge of our galaxy. Now, if you are on a spacecraft and you move outside our galaxy, imagine you do that, this is how our galaxy will look like. This is an image of the Andromeda galaxy. And what you will realize is that actually the Sun is not in the center. It's quite in the outside region of our galaxy. It's about 26,000 light years from the center. And there are about 200 billion stars in our galaxy. And what we know is that, as Laetitia said, that planets are very, very common. What you see here is an image of our galaxy, the Sun, and what you see here is the region where the Kepler space mission, NASA Kepler space mission, has monitored the sky to look for exoplanets. And assuming that the stars where Kepler has observed are behaving in the same way all over in our galaxy, there is no reason why a star over there should behave differently from a star in the region where Cheops has observed. We can certainly, if we find what is the occurrence rate of planets around stars, we can basically extrapolate it to the whole galaxy. And what we found is that planets are very common. About 25–30% of stars like the Sun host at least a planet. And this is a lower limit. We believe that the occurrence rate is even higher. So basically every star has a planet. But there is one issue, is that Kepler has observed mainly faint stars because it was a mission designed to do statistics. And what we want now is that we know that planets are everywhere. We want to have bright stars because we want to characterize them. We want to know what are they made of, how they form, how they migrate, how they evolve, how they interact with their star. And to do this, we need bright stars. And this is why we need Cheops. Cheops has been designed to characterize in terms of size planets that have been already discovered by other surveys, like the radio velocity survey that what Laetitia was discussing before. And so we know from these planets, we know the mass. What we now need to know is the radius. And those planets have been selected in such a way that the stars they are orbiting around have to be bright. And Cheops is not only designed to measure the radius, it will also give us very, very in-depth information about the atmospheres of those planets, as you will hear now. But let's now just recap. So on the top, you see what Laetitia has just shown us, the Doppler method, which is the provider of the planets for Cheops. So we have discovered planets using the Doppler method. We got the mass of those planets, and now we want to see if they are transiting the stars. Because if they are transiting the stars, if they pass in front from the depth of the signal, we can measure the radius of the planet. And once we know the radius of the planet, we can do this. I just go a little bit more into details. And this diagram, what you see in the x-axis is the mass of exoplanet, of known exoplanet, in Earth masses. And on the y-axis, you see the radius. This plot is showing you only planets that are smaller than Neptune. So what we call the small planets. So basically planets that have radii smaller than 4 radii. And I have prepared this plot a couple days ago, making sure that I'm going to show you here. So every gray dot points are known exoplanets. And I made sure that to show you here planets that have well-measured, precisely measured masses and radii, so that you can start see some difference. From your reference, planets like Neptune and Uranus are up there in this upper right corner, and the Earth and Venus and Mars are lower here, in this lower left corner. What you see here are models of planets with different composition. So imagine a planet just made of iron. A planet just made of iron will be on top of this line. And if you just reduce the amount of iron and increase the amount of silicate, the planet will be on this dashed line. And on the yellow-green line, you have just a planet made of silicate. And so on. You can start putting water, and then you can even have planets that are just made of water. And as you can see, those guys here, they don't seem to, on top, on the right top corner, they don't seem to belong to any kind of, how do you infer the composition? Why they are up there? Well, those planets, they actually have an atmospheres. So they are twins of those guys. And if you, on top of those guys, you put a thick atmospheres. If you put a thick atmospheres, you increase mainly the volume, not much the mass. The mass is in the core, which is heavy, it's made of metals, of irons. So by putting the planets in this diagram, we can get the composition of planets. And if we know the composition, we can tell what they're made of. We can infer how they form, because different composition reflect the region in the protoplanet nebula where the planets were formed. But Cheops is not only doing this. What you see here is a transiting planet, and you see that when the planet is passing in front of a star, you get a transit. And as I said, from the transit you can get the radius of the planet. But the planet at some point will go behind the star, and your photometric precision is high enough, you can see what we call the secondary eclipse, which is by the time when the light reflected by the emitted by the planet or reflected by the planet is covered by the star, because the star is in front of the planet. And if you go a little bit more in details, you can see that it is like, in this plot, there is like a wave, right? That is rising from the transit up to the secondary and then going down again. And what does this do is because while the planet is revolving the star, what you see here, that when a planet is in front of a star, you see the night side of the planet. When the planet is just behind the star, or right before it goes behind the star, you see the day side. And all the way in between here and over there, what you see is the changing phase. So you see a fraction of the night side, then you see the fraction of the day side increasing, and then the fraction of the day side decreasing, and then again the night side. And of course, this is changing the amount of light that is reflected by the planet. Now, what do we learn from this? So we call this wave-like signal phase curve. And what we can learn, this is actual data. This is what Kepler has observed. And Cheops will be producing this kind of data for many planets. What we can learn from the phase curve, what we can learn from the secondary eclipse, we can measure the temperature of the planet. We can measure how well a planet is reflecting the light from its stars, because you might expect that the amplitude of the phase curve depends on how well the planet is reflecting the light of a star. So we measure the albedo. Then we can also measure how the heat from the day side is distributed to the night side of the planet through winds. And now, I have been actually lying to you, because I said that Cheops will only provide the radii. This is not true. In some special case, you can also get the masses. So imagine you have a star, and there is a planet orbiting the star. Now, Cheops won't see a face-on system. Cheops will see an age-on system, so that you have transit. Now, as you should expect, the period is constant. So basically, a transit is occurring always at the same time after one period. There is no reason why this should not happen. Now, let's imagine that your system actually is not just only made of one planet, but you get two planets. So you got this inner planet and you have an outer planet. And let's see them, the system age on again. So what happened is that there is a mutual interaction between the two planets. So basically, the outer planet is interacting with the inner planet gravitationally, and is pulling and pushing the planets. And what happened is the transit do not occur always at the time when you expected to see them. So they occur either earlier or they could later, simply because of the gravitational interaction between the two planets. And we can measure this with Cheops because we can get precise timing of the transit. And if you see variation in the timing, that is what we call transit timing variation. And the transit timing variation, so what you see here is on the x-axis you see time. So you have two planets, an outer planet and an inner planet. In the x-axis you have time, and the y-axis you have what we call the transit timing variation. So how much the timing of the transit is changing with time. And you see that this is a signal that is repeated in time, and is actually you can measure the quantity, how much is changing. And from the amplitude of the transit timing variation, so how much the timing is changing, what is the time needed to see a full cycle, you can, first of all, you have found a new planet. So Cheops is going to find new planets. But not only this, you can also get the masses. And they come for free. You don't need to sit on a telescope on Earth and take a spectra of your star in order to get the mass. You can get the mass for free from here. And since you are going to discover new planets, you are going to infer the architecture of a multi-planet system. And this will also give us insight about how those multi-planet systems form and migrate. So I have to admit that I'm very, very, very excited to be working with the data coming from Cheops, because I'm sure that Cheops is going to do a leap forward in exoplanetary science. And I hope you will stay tuned for the first results from this mission.
Thank you, Davide. Thanks for showing us a little bit the exciting science expected from Cheops. What's going to be the result that will excite you the most?
You know, I'm a guy who likes to discover planets, so actually transit timing variation is something I like a lot.
Okay, so looking at, and actually that's one of the most exciting, but probably also one of the most challenging measurements, right?
It is.
So, good. All right, thanks. As a next and final speaker, we will have Isabel Rebolledo. I didn't pronounce that correctly. Let me pronounce it again. No, I did. Rebolledo.
Yeah.
So Isabel is actually not from the Cheops science team, the core team, but she's actually the principal investigator of a Cheops guest observing program. So as mentioned before, Cheops has a core science that it wants to actually perform and do, and that's going to be most of the time. 3/4 or more. But we also have reserved some slots for people who have brilliant ideas, and Isabel is one of these persons who had a brilliant idea, who proposed it, and is in this first cycle of first year of Cheops, will perform her observations. And her brilliant idea was actually not only to observe exoplanets, but also to observe exocomets. So she's going to tell us a little bit what that is and why she's excited about it.
Yeah, thank you. So actually, we assembled a team to do this. I'll tell you a bit about it later. But I'm going to go briefly through what exocomets are and what we plan to do with Cheops. So we've seen a lot of artist impressions. This is just one more, actually from TRAPPIST-1 that Leticia talked about. And they always look kind of like this. So you can have one star, two stars, and one planet or several planets, but it kind of always looks like this. And actually, when we are looking at planetary systems, the picture it's closer to this one. We have star, we have the planets, but there's a lot more stuff in there. There's rocks, there's dust, there's a disk of dust and gas. So all of that conforms the planetary system, and it has crucial input on how planets form, and also in habitability. If you have a lot of dynamical interaction, it's very unlikely that you will generate life on a planet. So we see planets and we see stars, but we also see the disks. So for example, this is real data from Hubble Space Telescope for one particular star. I'll be talking a lot, that it's Beta Pictoris, and you can see the star is blocked, the light from the star is blocked, but you can see the disk. So there is where most of the material of the smaller bodies are, and also the gas and the dust. But actually, when we study planet formation, we assume that most of the gas will be depleted. When you form a star, the disk that remains where planets form has a lot of gas and dust in the first stages. But as the planet formation goes on, most of the gas is depleted. So where is this gas coming from, actually, that we see in stars that have already formed the planets? So there has to be something evaporating. So the first time we saw actually something evaporating in a planetary system was in the 87, so years before the first exoplanet was found. And if you have a small body that it's evaporating, you would say it's a comet, or in this case an exocomet. But again, this was discovered in the 87, and there was no way they would call something exocomets, because we didn't have any proof at the time how exoplanetary systems were. So this is a plot from that paper where you can see the calcium-2 line. So there's different contributions here. You can see the contribution from the star. So that big tip, it's from the atmosphere of the star. You can see the contribution from the disk. So the disk I told you that has a lot of gas and dust is creating that contribution. And then you can see that for different line styles that correspond to different dates, we have different tiny absorptions there that correspond to the exocomets. So exocomets are really very variable. They depend on the day you observe. You can see them or not. Actually, we cannot tell which stars don't have them. We can tell where they have them because we have seen them. But if we don't see them, it doesn't mean they're not exocomets. It just means that maybe we're not observing the right time. And this system, again, it's very interesting because 20 years after the detection of exocomets, a planet was found. And this planet is consistent with being in an orbit that destabilizes the material in the disk and may throw it inwards. So those comets have probably a lot of volatiles and are far away from the star, but that planet, when it passes by, destabilizes them and throws them inwards. So you can have a picture more or less like this. We have the disk with a lot of gas, with a lot of dust. We have a big planet in the outskirts, destabilizing the material, and then we have the comets that reach the star in the center. And actually, this is pretty accurate because we have just found, where a planet has just been found again in Beta Pictoris, so it has 2 planets. But again, exocomets are really hard to find, so we have only seen them in around 25 stars. And this has changed a bit because we could only see them with these techniques in spectroscopy. But now we can also see them in photometry. And it was Kepler, the first one who found them. You can see here the light from the star, that it corresponds to the black dots and the straight line. And in the middle of the stellar light, there are some dips that, if you can see, they are not periodic. So that's the first clue. This is not a planet, but something different. And then, in a closer look, they're not symmetric. Again, second clue, this is not a planet. You have seen a lot of transits now that all my colleagues have shown. And this is the shape they have. A planet is symmetric, it's round, so it has a symmetric transit. You can see when it comes in. It's a sharp edge and then another sharp edge. But comets are not symmetric. They are more or less like this from comets in our solar system. So they have a sharp edge in the beginning, but then they have a tail. So this corresponds more or less to this. We have an ingress of the transit. So the beginning of the transit is more or less like the one of a planet, because the beginning of a comet, it's round, it's a sphere that corresponds to the nucleus. But then, as the comet passes by, we just see the tail fading away on the star. And this was actually predicted before the year 2000. So when we had already discovered comets and we knew there were around a few stars, Alain Le Cavalier suggested that we could see them in photometry. But we had to wait another 20 years so we could see them for the first time. And if you see it like backwards, it has like a shape, shark fin shape. And this is how it was called in this paper, where for the first time they found the exocomets that we had seen in a spectroscopy in photometry. So again, you can see that it has the sharp ingress corresponding to the nucleus, and then the egress corresponding to the tail of the comet. So in this context, when this has just been published, there was, for the first time, the first conference just for exocomets. And if you see the dates, it was in May 2019. It was coincident with the deadline for the guest observer program of Cheops. So there we assembled a team. You see that Sebastián Tieva was the one who published the detection of photometric transits of comets in Beta Pictoris, and Alain Le Cavalier who predicted the shape, are in the team. So we got together and we thought, is there any star that it's worth looking at that TESS is not looking at, or so on? And we got to this star, which is 5 Vulpeculae, 5 Bull. It's a very bright star. It's fairly close. 70 parsecs is like 200 something light years. And it's an adult star. It's in the main sequence. It's 200 millions of years old. But it's young enough to still have dynamical interaction. So bodies are interacting with each other. And there's probably a lot of small bodies in there. And it's also bright enough so you can see it at night if there's not much light pollution. But most importantly, it has comets. You cannot see the contribution from the star in this plot, but you can see the contribution from the disk. And you can see there's tiny variations, not as clear in Beta Peak because no star is as clear as Beta Peak when exocomets, when we're talking about exocomets, but it definitely has something. So our proposal was accepted, and now the question is, are we going to see something or not? So again, this is very variable. We can get a lot of time to look with Cheops and still not see anything just because that day exocomets decided not to pass by. But Cheops has two very important characteristics. One is that we will get a lot of data points, so almost 1 data point per minute. And we have a very high signal to noise, so the quality of the data is going to be very good. And those are the most important and principal ingredients for the detection of exocomets. And so we will have to wait a few months and a day now, and I'll let you know if we find something. Thank you.
Thank you, Isabel. I should have mentioned that Isabel is actually a local. She's from the Universitat Autónoma de Madrid. So you can actually walk into the control room, well, maybe past the security, but close to that. So how many systems will you be looking at? What did you propose
Just one, just that one.
So you're looking for one system to start with?
Yeah, just that one. Actually, we had to choose from the systems where we knew there were exocomets. We cannot just look blindly to the sky. And lots of them are already in the TESS field of view, but this one is not. It's just in the blank space for TESS. So, yeah.
Good. So, in fact, Cheops will have an opportunity every year, more or less, to apply for new time. So, if you see something, you could actually go on and then continue studies. Yeah. Good. So, we have time now for question and answers. So, I'll maybe ask all the speakers to come on stage. Isabel, you can stay here. Okay. If we maybe can get one more microphone and switch it on. What we'll do then, between now and we still have a cocktail and catering planned in about an hour and a half, I think, from now, is time for interviews. But we'll start here for general questions. If you have any general questions, please feel free to ask them now to our speakers. I'll give you one microphone here that you can pass around, and I'll walk around with a microphone. and then time for individual interviews after that. Any general questions from the audience right now to any of the speakers? General is as general as you want, and
Probably to Francesco. Will Cheops observe in white light? I mean, just the quantum efficiency of the CCD, or there will be any filter somewhere?
Yeah, indeed, Cheops will observe in white light, so there is no filter. So it will indeed from visible from 0.2 until 1.1 micron, so closing to the near infrared. Indeed, there is no filter, and this is done indeed to have as much a signal as possible.
First of all, thank you. I learn a lot. Even I should already know it. Now I have a question on the habitability concept. Is there a broad acceptance of it, or is it still a concept which is challenged among scientists?
So habitability concept, does anybody want to answer it? I can give you my quick answer. So I'm still an adjunct professor at the University of Munich teaching astrobiology, and I asked, and actually if you look at our other missions, so the habitable zone in the solar system encompasses the Earth, goes not quite to Venus, not quite out to Mars, but where we are looking actually for life is also on Mars and actually beyond Mars on some of the moons of the giant planets. So the concept of habitability originally started as liquid water on the surface. Whether that's absolutely necessary for life is debatable, and life is very creative. So it's a very broad concept. I think, as Laetitia mentioned, maybe misleading a little bit, because that's where we're going to look first for life, but it doesn't mean that life could not appear elsewhere. So that was the very general question, but maybe Laetitia can say something more intelligent about this.
Not necessarily more intelligent. No, I agree with you, actually. We're using this concept of habitable zone just to help us to narrow down our selection of potentially habitable worlds. And we are looking for liquid water because we know on Earth that this is really a key ingredient for life. But I agree that we could imagine all kind of, some other kind of exotic life. And so, yeah, we could have some surprise in the future.
But it's certainly a good starting point if you know that liquid water can exist on the surface. Other solvents other than water might also be suitable for something that we would call life, but then it leads to the philosophical debate of what you call life, what type of metabolism you really expect, and so on. Any other general questions? Yes.
I think the data archive for Cheops is done by the consortia in Geneva currently. Is there a plan to have the archive here at some point?
Okay, so that's a good question. I don't know if Bruno or anybody from the archive is here. So I don't know if somebody can answer. Anna wants to.
In the long term, yes. I mean, so in principle, as far, well, at least in the science management plan, there's a mention that indeed the long-term archive would be handled out of Geneva, but actually, of course, Geneva will have the main archive for many years and while it's funded and so on, and eventually it will be also in parallel, because when the data is public, so then it will also be able to join the ESAC archive, and so they can be accessed. But clearly, I think it's for the first 10 years at least is in Geneva and so on, and then eventually will join the ESAC.
And so maybe a general answer, why do we have archives in the first place? Is because very often we fly missions which are unique. You might not repeat them in 20, 30 or maybe ever years. And what we really see is building legacy for humankind. So we want to actually collect these data, put them into archive, and then eventually open them to the rest of the world. There's typically, to acknowledge actually intellectual copyright, there's a proprietary time. In this case, I think it's a year after the last measurement for an object is taken for Cheops. So that's when the science team can actually exploit the data, because obviously they propose, they have the mission, etc. But afterwards, the data are open to the rest of the world. Because the mission, the science operations that are in Geneva, we will actually host the archives there. So they're going to nurture the data, make sure that they're actually of excellent quality to be given to the rest of the public. Eventually, in the long term, ESA, we don't expect the member states to finance the archives forever. We have the infrastructure here, actually on this site, to host them forever, I mean, whatever that means. And we will actually then recuperate the Cheops archive eventually here, that's the plan, and then keep it then for the rest of times there. The mission itself is a mission, Cheops is planned for 3.5 years. It can be extended a little bit, but then eventually there are consumables on board, which will actually fade. So I think the total length maximum will be 5-6 years. Then some scientific exploitation beyond that, but then actually also the funding in the member states will be used for other missions, exciting things. We at ESAC can actually then keep funding our archive because we build on many other archives that we have hosted here. So, and I saw a question in the back over there.
I see how you get the high precision ratio of the radius between planet and star from the photometry. How well do you then know the radius of the star to get the radius of the planet?
Can I answer this one? For many systems, we are still at the level when what really counts is the precision of photometry. So I expect that with Cheops, we will reach the level where what really matters is the precision on the radius of the star. We will be using the data coming from Gaia to precisely determine the radii of stars. That would be a strong asset for the entire mission. But as I said, we will reach the level where really what will dominate is the error bar, so the uncertainty on the radius of the star. This is our aim, and the precision we get with Cheops will allow us to do this.
Well, thanks. Let me expand on this question maybe. So we showed, and I think it's true for many of the science we do today, very often it's not a single experiment which will give you an answer, but you combine many other experiments or missions or telescopes, etc. So which are the most important contributors to actually enable the science of Cheops? So which other telescopes, facilities, on which results do you build? Anybody wants to take a take?
As I said, certainly Gaia will provide the radii of stars, but we also need to get the masses, and those comes from radial velocities. We'll be using data from HARPS, Espresso, HARPS Nord. So those spectrographs that allow us to get precision better than 1 meter a second.
So these are all ground-based telescopes which are operated. Actually, many of the ones you mentioned were actually European. I think also the Europeans took the lead at some point and started to build a whole armada of armada is maybe the wrong word. That's for these space ships, but group of actually instrumentation on telescopes both in Europe. Carmenes was not mentioned. Huh? You wanted me to mention that one in Spain, of course, at the Canal Alto. And the other ones were European Southern Observatory instrumentation. And indeed, we actually have a very strong legacy here in Europe to actually get this radial velocity data that are then combined.
But the good news is that the planets that Cheops will be observing are system where the mass of the planet is already well known through radial velocity of Doppler observation. So we will be using the legacy coming from years of observation done with ground-based facilities.
Good. Any other general questions in the audience? You want one more? Okay.
Thank you, Marcus. It's regarding the Cheops Mission Consortium reserved target list. It is not I suppose that you have discussed this for days and days and days. The thing is that ESA has the list, the consortium has the list, and that in the open proposal section there is a tool for knowing if your target is in your list. But why not making it public at the beginning, or?
Does one of you want to answer that? I can give it a general answer. So in general, the field of exoplanets is extremely competitive, I think, and many groups, of course, want the first. Maybe now that the Nobel Prize was given for it, everybody will relax a little bit more. There might not be a second prize to win, but I think it's interesting to see this at the same time collaboration in the field and this very high competitivity. And I think all the players hold their cards very close to their chest, right? So it's understandable that the group doesn't want to publish the entire list because that might show for which objects they have the most interesting data, and others might want to chase these planets first. And since you need very often to follow up on the planet to actually get all the subsequent information, I think it's understandable also that within the proprietary time you hold this close to your chest. You can, if you want to, could rebuild the list. Also, I must say that the list is not completely finalized. They still have a little of window to the science team to actually finalize that list. Also because we have ongoing, Exoplanet is a very active field, so there's ongoing observations and they want to actually continue to include it. Eventually we're trying to work in the best interest both of the community, so actually giving all the information possible to the community, but also respecting the interest of the science team, so making sure that the copyright, the intellectual copyright is respected. And so trying to find a balance between these two is always a little bit debatable. And on both sides, if you're in the community, you might say like, oh, we would like more information. If you're on the side of the consortium, you say like, I would like to give a little bit less. We think we have at ESA found a good compromises, doing justice to everybody. So at the moment we perceive it as fair. I can understand that if you sit in the community, not in the science team, you might want to have more information. Yeah. Not with Cheops, but if you know, but people might actually prepare for follow-up observations once the Cheops data are out. I don't know. There's one of the science team maybe members want to answer that.
I just would like to add that we do have a protected target list that is not frozen. So with TESS is flying, is providing targets, but TESS doesn't have the same precision as Cheops. So we might want to improve the precision on the radius using Cheops. So if TESS finds something where the precision is not good enough, and so in that case, we pick up that object and add it to the target list. But we have been very, very fair because this is also going to be a mission open to the community. So on the protected target list, you see only those targets that we believe being the best in terms of science, and we are not protecting targets that we do not observe. In other words, let's suppose I have this target and I'm doubting whether it's interesting or not. I want to take more time. I just put it in the protected target list, so at least I have more time to think about it. No, this is not how it works. If you protect it, it's because this target is in the schedule and it's going to be observed.
Yeah, so I think that's another, we made sure that actually they don't protect the entire sky and nobody else can observe anything, even if they will never look at it at the consortium, right? So I think we found a good middle way of fairness there. Any more questions? Otherwise, we'll give all the journalists here the opportunity to interview us individually. We can provide for interviews in Spanish, Italian, French, German, English, any other languages that you feel comfortable in. All right, good. So we are here at your disposal. Thank you very much, everybody, for joining us. We'll have a cocktail a little bit later. I think I don't see my colleagues here, but we might organize a tour for the ones who actually haven't been at ESAC before and would like to see a little bit the site and what we're doing here. And I hope to see you then around 1:30 for the cocktail here. We'll have a I'm not sure we're going to open champagne, or maybe just because we have it and we want to. But certainly there's going to be good food and other drinks as well. Good, let's resume then after that. And we'll stay here and grab us if you want interviews for us. Thank you.